First of all, thanks a lot to the organizers for organizing this conference and giving me the opportunity to present something here, especially since it's a joint work with Claudio. What I'm going to talk about today has to do with dynamical fluctuations at a critical point defined in a certain way that I'll make precise for a certain small class of interacting particle systems. But before I go on to talk to you about this, I'd first like to take a step back and give you some context of the kind of problem we're interested in and how this relates to that. So let's start with some motivation. And to do so, let me look at another model that doesn't have anything to do at first glance with this one, which is the Ising model on a box. Let's say, for instance, here in Z2, and you can imagine there's periodic boundary conditions. So this is the box. And the model would be a probability measure, mu beta, with a weight proportional to some energy functional, where sigma is an assignment of so-called spins plus minus 1 on the nodes of the lattice. Beta is a positive parameter, and my energy functional in the present case is just going to be the sum of the nearest neighbors with a ferromagnetic interaction. Now for this model, as many of you probably know, there's something called a phase transition going on, in the sense that the behavior of this measure when the size of lambda goes to infinity is very different depending on the value of beta, at least in high enough dimension, here dimension larger than 2. For instance, you can understand this as so there's a certain value beta critical, that I'm going to say a few things about in a second, such that if you have weaker interactions, so if beta is smaller, you have short distance, exponential decay of correlations, so short distance correlations. Whereas if you're bigger than this value, stronger interactions, then you have long distance correlations. Now it's not so much the model itself that I want to talk about, it's the dynamics in this model, which would be natural Glauber dynamics, where a configuration is turned into a configuration with the spin at position I that has changed sign. I hope the notation is clear. So I just flip one side at rate. Let's say, let me take a specific formula, but it doesn't really matter. So that would be the rate for my dynamics. And I look at the dynamics that's reversible. So this dynamics is reversible with respect to my measure. In particular, the law of the dynamics converges to it in long time. And the question you can ask is, how long does that take, and what happens to the dynamics? It turns out that this critical parameter plays an important role in that picture, because what one can, well, depending on the case, is either prove or at least give strong arguments in favor of, is that if you're at a high temperature, at a low enough beta, then the convergence, the speed of convergence, defined in however way you want to, does not depend on the size of your lattice. On the other hand, as the other extreme, if you're at low temperature, so high beta, convergence is typically exponentially slow. And the situation I'm going to be interested in this talk, although for a much simpler model than this one, is what happens precisely here, at the critical point. In this case, if you start at a higher temperature and somehow lower it, what you'll see is something called a critical slowdown. Which manifests in the fact that your speed of convergence starts depending on the size of your lattice polynomially. So that's the picture for the Ising model, but in fact the Ising model is just one particular representative of a huge class of models for which a similar picture is supposed to hold. So there's a whole theory of different possible behaviors at the critical point, different universality behaviors, depending on your dynamics, depending on whether or not you have conserved quantities and the relationship between conserved quantities, order parameters, and all that. And there's an impressive or inspirational paper by Hohenberg and Halperin about this, a review paper, which dates back to 1977. But it's very hard to make any of this rigorous. Even for the Ising model, there's some gaps there. Even understanding what exactly is the exponent here of this polynomial is very hard. So my goal in this talk is going to be to present one model for which we can say something about what happens at the critical point, and to give you some more context. In the Ising model, people have managed to say things, but in simplified settings, what makes things really difficult here is the fact that your energy H is local. So the interaction is between nearest neighbors, and your graph is very complicated. If you make your graph much more dense, or if you make the interaction much longer range, which is the same, actually, let me do that. Then it's people understand very well what's going on. All right, so what people know is, for instance, what happens in the so-called mean field case, where your energy functional is a sum of the nearest neighbors. Sure, but you've changed your graph. Everyone is a neighbor to everyone else. So you're on the complete graph now. Stay with the same sign. Then critical slowdown is established, and you can even get scaling limits for instance, the behavior of the average magnetization. This is a very simplified setting. People still manage to do something in a rather more complicated one, which is a so-called Ising model with Katz interaction. It's still long range, but the range of your interaction is parameterized by some function. Let's call it J. And you tune the size of your box depending on this parameter gamma, which you think of as going to 0. And then you can still describe the scaling limit of an object such as this, and it's related to models from Euclidean field theory, so-called 5-4 models. This is much, much, much harder, and has only been done, so in dimension 1, it's been done 25 years ago by Rüdiger, Saada, Bertini, and Presutti. But the two-dimensional, three-dimensional cases have only been achieved rather recently, thanks to work of Hendrik Weber in particular. Now, the setting I want to consider is a setting in which one has genuinely short-range interactions in here. So we're going to need something to make our life, well, to make it possible still. So let me introduce the model I'm going to be discussing. I'm going to look at a one-dimensional model on the unit torus with n sites. Let me write this as a Tn. So just one-dimensional model, periodic boundary condition. And my dynamics is going to be described by a generator I call L, acting on test functions as follows. let me write it down completely and then tell you what the different terms stand for. So here in this expression, eta is just a particle configuration. I put either 0 or 1 particle on each side of my torus. And then there's two pieces in my dynamics. This is a Kawasaki or symmetric simple exclusion part. This one is the reaction term. It's similar to the Glauber dynamics from before, and to make the connection with the Ising model, I described just, which one? This one. I described above. Let me choose a specific form for the rates, which doesn't matter so much for what I'm going to say afterwards. And here, let me also add that A is just some parameter that I can think of as being small for now, because I see my reaction part as a perturbation of the exclusion part. Now, in my notations, what I didn't say is that this eta with two indices, I plus 1, is just I'm making an exchange of particle, or of the state of one site with the nearest neighbor in 1. As usual, in the second one, eta with superscript I is the same as before. I'm just flipping or adding a particle if there was none, or vice versa. So my jump rates, I'm choosing them in a certain form that I'm going to write as a function of an additional parameter like this. Where here I find it convenient to recenter my occupation variable around 1/2, so that this is just plus 1/2 or minus 1/2, looks like a spin from before, especially if you multiply by 2. And gamma is just some parameter that I think of as being a hyperbolic tangent of a certain parameter beta. And if I do this, the dynamics with those jump rates is precisely reversible with respect to an Ising measure on the unit torus, which is, well, of the same form as before, in one dimension. I guess I should write with an eta, and then there's a 4. Okay. So what does this model have to do with this behavior I described above, the existence of a critical point, or what's critical in there? Well, in order to answer that question, let me describe what each piece of the dynamics is going to do. If you just look at the exclusion part, and assume that A is equal to 0, you just have the exclusion, then well, it's just a symmetric simple exclusion process. So it's going in long time to converge to something that's uniform, or to a product Bernoulli measure if you start it in a product way. So it wants to spread all particles uniformly. If I just look at the reaction part, let me call it Glauber. Well, I just said it converges to this mu beta, one-dimensional Ising model. This is not a very interesting statistical mechanics model, this one-dimensional Ising model, because it does not have a phase transition. Now, what's much more interesting is that if you put the two together, this symmetric simple exclusion Kawasaki part is actually going to average things in such a way that effectively you have long-range correlations, long-range effects, and the invariant measure of this model is not this short-distance Ising model, but something that looks like a mean field Ising model. This is a heuristic that was already observed by the people who introduced this model in the 80s, as far as I know. It's De Massey, Ferrari, and Leibowitz, and who also proved quite a lot of things about it. So the invariant measure is, in some sense, that actually most of this paper is about making this connection precise. It's some sort of mean field Ising model, which does have a phase transition. Okay. Yeah. Everything, yeah. Okay, so at this point it's just heuristics. I'm not proving anything, but let me tell you what is known already about this model. And in particular, this will give me a way to substantiate what I say about the existence of a phase transition for this model. What is known and was proven by these people, albeit in a slightly different setting, but much more generally than this one-dimensional case I'm talking about, and I think this was 1986, is that you have, you can describe the typical behavior of the density of particles in your model. You can prove a hydrodynamic limit for the density of particles. So if you look at the empirical measure, let me write it like this. So it's a random measure. Which puts a Dirac point at each of the lattice side. And you count whether you have a particle or not. This object actually converges in a rather strong sense to the solution of a certain PDE, where this PDE is a reaction-diffusion PDE. Let me write it like this. And this V prime, I can write it explicitly, provided I find the expression in my notes, like this. Okay, so it's perhaps not so clear what's going on here. Let me make a picture of what this function looks like.
You need A in front of the reaction type.
Yes, thank you. There's an A. So what does V look like? I'm plotting V, not V prime. I don't really care about the constant, but I don't really care about the constant. So as you can see from the expression here, this V prime is going to be, this V is going to be fairly different depending on the value of gamma. If gamma is smaller than 1/2, and remember that this parameter gamma is our effective temperature-like parameter here, so think of this as varying the temperature when you vary gamma. The potential has a unique minimum at density 1/2, and it's uniformly convex, say. So it looks like a single well, looks like a Gaussian. If you're above this point, the derivative of your V prime still vanishes at 1/2, but now there's two value, symmetric, and your potential looks like a double well. And precisely at gamma equals 1/2 is when, this is a bit hard to represent, have to convince yourself that this is not the same as this. The potential is quartic at the origin. Well, actually not close, it's quartic everywhere, but so it's quartic around rho equals 1/2. So it's this change, if you want, in terms of, well, so what happens precisely at this point is that this unique global minimizer of the reaction term loses its stability. And it's this stability that we'll interpret as a phase transition, and that's going to have the same effect you usually see, for instance, in equilibrium phase transition of a different scaling, non-Gaussian scaling for fluctuations, or this kind of thing. Non-linearity is appearing. So that's this point that we want to describe, what happens here. Before I go on to tell you what we can say, let me mention that much more is known about this model than just this. Actually, already in this original paper, these people showed that at this point, there is some kind of instability in the sense that they can prove a central limit theorem with a covariance that they show blows up in long time. So you have Gaussian scaling, but unstable. And in a way, what I'm going to say afterwards is identifying exactly how it blows up. So what's the correct scale for the fluctuation? This model has also been studied recently from a different perspective, from the point of view of cutoff that Justin mentioned. Justin, well, did more than mention, by Rencontres. So cutoff is known in the setting I'm talking about all the way to the critical point. So all the way to this gamma equals 1/2. And lastly, something we'll hear about some more in the coming days, in talks by Funaki and I believe Tsunoda as well, is what happens at low temperature. Because you can start playing with the strength of the reaction term and study how interfaces separating regions at different densities, either rho minus and rho plus, form and propagate. So here I'm only focusing about this critical point. So what can we say? So if you look at what I wrote above over there, the holy grail, you could say, is understand what happens at the critical point. So how much time does your dynamics take? How does it slow, first of all, and possibly what does it look like? Turns out that this model is sufficiently simple that we can both say how much time it takes to converge and what it looks like. So the observable we're going to look at is this random object, which acts on, say, a test function f by, okay, let me not write it right here. Let's say there's a certain rescaling in space, a certain rescaling in time, and I'm interested in the behavior of this object when n goes to infinity for a suitable choice of scaling. So the claim is that if you take a time accelerated by square root n, which means your dynamics has a generator square root n times what I wrote over there. I accelerate the full thing. If you rescale in space by the Gaussian scaling times something more, because fluctuations are bigger at the critical point, so n to the 3/4 instead of the square root n. And if you're at the critical point up to some small window of size 1 over square root n, parameterized by an additional theta, then what you can prove is the following. I'm going to change my blackboard. I'm going to make two separate statements. First one is, suppose you have a small reaction term. The reaction is a small perturbation of your exclusion dynamics. In this case, what you can prove is that actually this yn it projects on the mean, which means that for any test function on your torus, if you look at a finite time window and you compare this minus fluctuations of just the global number of spins, this goes to 0, where m and t is just the suitably rescaled fluctuations of the number. So somehow, everything that fluctuates at this scale has to do with the mean. And the mean, we can say, it converges weakly to the solution of a nonlinear stochastic differential equation, which reads like this. And I'm forgetting the square root thing. So the total number of particles fluctuates in a non-Gaussian way. It satisfies, its evolution is given by nonlinear differential equation. What makes us possible to say this is that our model is sufficiently simple. And what sufficiently simple here means is what you're going to learn after I've erased one blackboard. Let's say this one. Is that actually this total number of particles is the only observable that behaves in this anomalous non-Gaussian way. What that means is if you take your function f, sorry, it should have been in, well, let's call it h. Take it with mean 0. Then it turns out that you can rescale your fluctuations in a Gaussian way. And prove that yn converges, here in the sense of finite dimensional distributions, to an explicit Gaussian random field which is stationary. It's a stationary Gaussian field with covariance that I'm going to write here. Here I'm only taking functions with mean 0 for this h and this other test function g, and the covariance is just this. Okay. So I'm going to comment on this and explain a little bit what this means. But before I do that, let me mention that actually this restriction that A be small is not necessary up to something we don't know how to prove yet, but that doesn't really have anything to do with all this. And it's a certain log Sobolev inequality that I may have time to say a few words about towards the end. So there's nothing essential to taking A equals to, or to taking A small. I have 15 minutes left, is that correct?
Yes.
Okay. So let me make a few comments about that result. First of all, if you look at these, there's a big difference between the fluctuation of this number of particles and the rest. This is one way of saying that the system is mean field, so to speak. There's only one thing that goes wrong when you have the phase transition, that's the fluctuations of this guy. All the rest is nice, and you can actually see it in here. If you're used to proving central limit theorems in interacting particle systems, you usually would have correlations in time. Here, the time variable is the same here and there. So the time variable of these fast modes is actually not at all appropriate. They still evolve on the diffusive time scale that was written on the generator over there in this n² time scale, but I've accelerated everything else, which means there's enough time to decorrelate in space, and that's what this indicator function means. So my field is stationary in time because actually at any time increment, I've already converged to equilibrium for these guys. The result I'm only stating for this particular choice of jump rates, but it doesn't really matter. So that doesn't matter. You can also say something in higher dimension, at least in this regime of A small. For general A, that remains to be seen. And since there's only one observable that converges to something nonlinear in the limit, I just get an SDE here. If you compare with what I wrote before about this Ising, well, I didn't write it actually, I just said it, but this Ising-Katz model, the convergence was to a much more complicated object, which was this infinite dimensional singular stochastic partial differential equation. See, here somehow we have the baby version. It's just 1 point. That's because of the global time acceleration, which is over there. The fact that we're accelerating time by square root n, we are also accelerating the diffusive Kawasaki part. That's what makes our life much easier, but that means there's only so much we can see. In the remaining time, I'd like to give you an idea of how the proof works. Yep. Answer in a minute. The relevant scaling is very easy to see. You just write the equation for, say, the magnetization, so this total number of the fluctuations of the total number of particles, and you get something that doesn't look so great, but if you assume you can just close these equations, or write a closed equation in terms of the magnetization, you see what scaling you're supposed to put. So, in more rigorous fashion, let me write exactly that. That'll be my starting point to tell you what we need to prove. Okay, so I want to prove some limit theorem for this object, the total number of particles suitably rescaled. I'm going to already write things assuming this rescaling, but you could deduce it from what I'm going to write. So let's say I apply my generator to this object. What do I get? Why am I doing that? Because as many of you are familiar with, if I want to obtain an equation for this, I write it semi-martingale representation, which is exact at any value of my scaling parameter. And then, well, actually, I guess I can just do it. So I have this identity. What identifies the correct scale is whether this is of order 1 in the limit and whether the martingale is non-degenerate. That's the two information I need. Let me forget about the martingale, just look at the expression of this guy. If I apply my generator to this object, I get two terms. The first one is this, which is just 0, because the Laplacian of the sum, I mean, I can make as many exchanges as I want. Let me put the Laplacian outside. This is going to be 0. So that's the exclusion part. And then there's the reaction term. And this reaction term, it looks like, what does it look like? I guess it looks, yeah. It looks like this. That's the first term you already see in the equation. This one comes from for free, and the problem is this one. And I believe in particular, the equation you get is not a nice closed equation on the magnetization. This is why these models with long-range interactions were so much easier, is because you basically got a closed form for free. Here, the hard part of the work is making this a function of this. But if you believe you can do that, that's how you get the scaling. So if you just think that this should be mn cube, and you work out the correct scalings, then you see that you had to put the square root n time acceleration, the n to the 3/4. So at the end of the day, what we want to prove is that when I have this time integral, with square root n, prove that, say, this object vanishes. And the question is, how do you do that? This is one instance of the so-called replacement lemma, or Boltzmann-Gibbs principle, and people by now understand how to do this. People by now understand how to do this. The difficulty here, compared to what's usually done, is that you have this accelerated time. So you're looking on very, very long time scale, which means you need to control very precisely what the constellations of this object are, so that this is actually small. And this is where we need quite heavily this global acceleration of the fact that we multiply everyone by square root n, so that the exclusion part is going to mix very, very strongly. If it mixed just a bit more weakly, so if we slowed it down just a little bit more, we wouldn't know what to do. Concretely, how do we control this? 5 minutes, right? How do we control this? Using the so-called relative entropy method. I'm just going to have time to give you a sketch, an idea of the three main ingredients, let's say. So this relative entropy method is what you resort to, or what you can resort to when you want to prove such a result and you don't know, for instance, the invariant measure of your process. This is the case here. We have no idea what the invariant measure is. So we are trying to prove this by saying, well, actually, this object is close to that because this, because my dynamics is very close to equilibrium in a suitable sense, and at equilibrium, this is true. Now, why does this have a chance of being true? It's because if you look at what this term corresponds to, and you think of eta bar as being a function of space, then this minus this is nothing but this function of space minus its lowest order Fourier coefficient. So all this involves Fourier modes that are non-constant. And what do we have that precisely handles convergence of all non-constant Fourier modes in our equation? This Laplacian here. That's why I wrote it even though it's 0. So this exclusion part. Concretely, how you see this effect in the relative entropy method, that you're trying to approximate the law of your dynamics that you don't know by some measure nu. Let's call it a reference measure. And you compute the so-called relative entropy of the law of your dynamics with respect to nu, which is just this ft log ft. And there's a formula for this, up to negligible losses, let's say, where this quantity, its time derivative, is expressed in terms of the adjoint of your generator in the spectral space, in the L2 space corresponding to nu, plus a dissipative term, which is negative. Let's call it like, okay, let me write this like this very roughly because I need to stop. Let me just say this is the sum on all the possible jumps of the dynamics. This is your Dirichlet form, if you want. So the way you make use of your exclusion part is by smuggling as many terms as you can from this guy into this negative term. And I thought I would be able to go a bit further. I'm sorry that I have to stop here before actually telling you what we do, but I'm happy to say more if you have any questions.
Okay, well, thanks, Benoît, for a nice talk. Other questions?
Very nice. I mean, I have actually two questions. So one question is, if you go away from the critical point in your model,
Yep.
I mean, then you sort of see the trivial behavior, exponential decay, and all these kind of things, or is that not true?
It's still a mean field easing model, sort of. You see Gaussian fluctuations, but you still have long-range correlations.
Yeah. Long range in space or in time?
In space.
In space, yeah, and that's sort of
yeah.
the related question. I mean, you sort of, somehow you didn't say very much about the invariant measures. I mean,
yeah.
But I mean, you have at least sort of a picture of what they look like as you go through this, you know, the three cases which are sort of still at the board, or?
Yeah, so I'm sorry, that's the case I didn't have enough time to discuss. So what it looks like, not very precisely, but at high temperature, for instance, you can make a very good approximation of this object by saying that it looks like a mean field easing measure with subcritical. But not just mean field, since your measure is going to be of the form exponential sum of eta bar I, eta bar j, gij, for some function g, actually, I guess I over n minus j over n. You can even do even better than that. You can just keep, instead of recentering with respect to 1/2, you can recenter with respect to the actual mean and do a better correction than just this approximation, which is, if you want, the Hessian of the right thing that you should put. And actually, yeah. So in a sense, the more problematic term is the magnetization, so the mean zero part of this function. That's the only thing you need to put in your reference measure to get the result when A is small, at the critical point, but also at high temperature. And then if you want to get general A, you need to understand a little bit more about the interaction between this zero mode and the higher modes. And that's where you get the full function g. This function g just being, in the particular case of the critical point, it's basically over there. You see the covariance term above. If you write this covariance as 1/4, which is 1/2 times 1 minus 1/2, it's the mobility, plus k. That's the covariance. It's the same as this. Because it turns out the covariance matrix of a measure such as this is that. And so you can identify, since I've given you k above, you can identify the g. So you get a strange equation on g when you do this relative entropy method, but really it's just this term above.
I mean, sort of static in your model looks, I mean, there's no spatial degrees of freedom anymore, right?
No.
So, yeah.
It is infinite dimensional, or mean field. Yeah, there's no space. That's why it's doable.
Are there other questions?
You said that you need a very strong Kawasaki mixing part to control long time behavior in this last time. But it is not already the case that you need this strong scaling for having the 86 theorem.
For having which one, sorry?
The 86 theorem, the massive
no.
Okay.
Much weaker.
Okay.
Yeah. So if you're only interested on things on a finite time window, so yeah, this whole theorem is about a diffusive time scaling. So you're only dealing with a finite time window, doesn't scale with your parameter, and then on finite time window, it's you don't need it. If you want this log Sobolev, so this very precise long time control is only needed because of the diverging time window. So no.
Yeah.
But I can try to make this clear afterwards if you're interested.
Are there other questions? I might ask, is there a way to get the nonlinear term when the mean of h is 0?
Yes. But so the simplest way I can think of, but I do not want to do it, is you see, if you look at the two parts of the dynamics, there's one which is effectively at temperature beta, that's the reaction part, and there's one that's at infinite temperature, that's the exclusion part. Simplest thing you can do to see something more interesting than a one-dimensional object is to add a temperature dependence on the exclusion part. Say mean field, temperature dependence, so there would again be only one mode that slows down the transition, just one object, the rest would be at infinite temperature. Then you can run exactly the same thing, except you have two objects to deal with. I cannot guarantee that everything does go through, but it should. And for sure, the log Sobolev inequality, so the log Sobolev inequality we need, for instance, for general A, is for suitable measure, for suitable canonical measures, so this mean field easing measures with canonical constraint, then you would need two constraints in the way the proof is done, and I don't know any result about that. So it's even less known than, but in theory, yes.
Thank you very much. If there are no further questions, why don't we thank Benoît again.